So, thanks to the organizers and good afternoon to everybody. I'm Eleonora Giovannetti and today I will talk about the quantum behavior of the anisotropies for a Bianchi-Knight model in a bouncing picture. In particular, this talk is based on this paper in which we investigate the possibility to avoid the unlimited growth of the anisotropies arbitrarily close to a bouncing point. This is a brief outline of the presentation. I will start with introducing the two main technical instruments that we use in our investigation. Then I will focus on the core of the analysis, that is about the quantum behavior of the anisotropies, and then I will outline some final remarks. So let's start with polymer quantum mechanics, that is an alternative representation of quantum mechanics that we use in our investigation. It is not equivalent to the standard Schrödinger one, but can be introduced by following these simple steps. In particular, one chooses a basis that is orthonormal in the Hilbert space with a parameter mu that is a real parameter. And then one introduces these two main operators, the label operator that acts in this way, and so that it is discrete in the sense that the set of its eigenvalues is related to states that are all orthonormal. And then the shift operator that acts in this way, and that is discontinuous in the sense that after its action, the final state will be always orthonormal to the initial one, no matter how small is this parameter lambda. So the importance of polymer quantum mechanics in cosmology is the fact that it is able to implement some cutoff effects. In particular, it is able to reproduce loop quantum cosmology phenomenology with a simpler mathematical formalism. And the important thing is that if we choose as discrete our configurational variable that in cosmology is often a geometrical quantity related to the scale factor, the volume, the conjugated operator does not exist. And this can be shown, for example, for a one-dimensional mechanical system in the momentum polarization. We can see that the Q operator acts in this way, in this polarization, and corresponds to the label operator, so it's discrete. And that the shift operator has this exponential expression with the consequence that since it is discontinuous, P does not exist as a well-defined Hermitian operator. So the standard procedure in polymer quantum mechanics is to introduce a polymer lattice in order to regularize the theory. Mu is the fundamental length, that is the polymer parameter. We can, obviously, in order to deal with a well-defined dynamics, we have to introduce a regularized version for this operator that is not well-defined. So we restrict the action of the shift operator on this lattice that is well-defined, and we introduce a modified version for the momentum operator, in this case by means of the same function, so that we can deal with a well-defined Hamiltonian, and we can study the cutoff effects in our cosmological dynamics. The second instrument that we use is the Vilenkin approach that comes from the need to solve the wave function interpretation puzzle in the Wheeler-DeWitt formalism. The starting point is the splitting of the phase space into two regions, the semi-classical one and the quantum one. In particular, the main hypothesis is that the quantum region is small and the effects on the semi-classical region are negligible. In this case, we can recover a time evolution because the quantum fluctuations are negligible. Therefore, since these two regions are orthogonal, we can write the universe wave function in this way. In particular, this is the semi-classical part of the wave function with S that is the semi-classical degree of freedom, and chi that is the quantum part. And in particular, this contribution is VKB expandable in H bar. Then the last hypothesis is that the dependence of chi on S is parametric, so basically it is a Born-Oppenheimer approximation on the universe wave function. Then by using these three hypotheses from the Wheeler-DeWitt equation, we can obtain order by order three different equations. At the zero order in each bar, we obtain the Hamilton-Jacobi equation from which we can derive the phase S of this wave function, that is basically the classical action. Then at the first order in each bar, we obtain the amplitude A and from the continuity equation, and we also obtain the Schrödinger equation from which we can derive the wave function chi, that is the quantum part. And in this way, we have obviously recovered a time evolution for our quantum system by defining a time variable by means of the semi-classical degrees of freedom, and our probability is positive defined and well conserved. So in our work, we put together these two approaches. We take in consideration the Bianchi-Knight model as our cosmological background. In particular, we consider the Bianchi-Knight model is the most generic, homogeneous, and anisotropic model. We expand up to the second order its potential that depends on beta plus and beta minus that are the two anisotropies. Also, in order to introduce the cutoff effects, we consider as discrete the universe area, that is A, and consequently we regularize the associated momentum, that is PA. And then, in order to introduce also the Vilenkin approach, we split our phase space into a classical phase space and a small quantum one. In our analysis, our classical degrees of freedom are the universe area A and the free scalar field phi, whereas our quantum degree of freedom are the two anisotropies. So, in our analysis, we were able to derive the three Vilenkin equations. The important thing is that polymer quantum mechanics is mainly formalized in the momentum representation, so all the Vilenkin approach has been reformulated in the momentum representation in order to make it compatible with the polymer formulation. Here we have the zero-order equation, that is the Hamilton-Jacobi equation, from which we can derive the action S. Then at the first order, we have the continuity equation from which we can derive the amplitude A and characterize the semi-classical part of the universe wave function. Also at the first order, in each bar, we have the Schrödinger equation that describes the time evolution of the two anisotropies and from which we can derive chi, that is the quantum part of the wave function. So let's start with the dynamics of the semi-classical sector. So why we have introduced the polymer quantum mechanics? Basically, we want to reproduce the bouncing behavior in the background. So this is the semi-classical part of the Hamiltonian with our classical degrees of freedom that are phi, the free scalar field, and A, that is the discrete universe area here. So in order to solve the dynamics, we fix the time gauge. Here we have the Hamilton equations. And then by fixing the initial conditions, we find the evolutions for the universe area and its conjugate momentum. As you can see, the singularity is removed and the universe area experiences a bouncing behavior. So the universe first collapses, then reaches the bouncing point, and then expands without reaching the singularity. So this analysis shows that by considering as discrete the universe area, polymer quantum mechanics is able to reproduce a big bounce. At a quantum level, we have recovered a Schrödinger equation thanks to the Vilenkin approach that governs the behavior of the two anisotropic degrees of freedom. Here you can see that the Schrödinger equation in this case is a time-dependent harmonic oscillator. And the crucial point of the analysis is that thanks to the presence of the potential, that is this term in brackets, that is not the exact Bianchi-Knight potential, but is its expansion up to the second order, we have that the polymer effects that are applied to the semi-classical background, because our discrete variable is the universe area and it is our semi-classical degree of freedom, enter also in the quantum dynamics because the time-dependent frequency of our harmonic oscillator is the universe area itself. So by changing the behavior of the universe area in time, we change the eigenstates of the harmonic oscillator. So in this case, we have solved this harmonic oscillator and found the eigenstates, and here you can see the associated probability density, by considering the bouncing behavior for the universe area, as I showed you before. Now we have all the ingredients to compute the mean value and the variance of the anisotropies and to analyze their quantum behavior arbitrarily close to the bouncing point. In particular, we have exactly computed the mean value and the variance by using the action of the creation and annihilation operators on the eigenstates. So obviously the mean value is 0, so if we consider the universe in one of the eigenstates or in a Gaussian superposition of eigenstates, we are basically considering the universe in a quasi-isotropic state. And the variance takes this expression, and as you can see, for different energy levels, the behavior is confined and as an oscillatory character, arbitrarily close to the bouncing point too. So in this case, if we start with a quasi-isotropic state for the universe, we have that the anisotropies are under control during the evolution. Also, we have computed the mean value and the variance also for the shear quantity. That is a quantity that accounts for the anisotropic character of the model, since it is basically related to the gap between the three Hubble parameters. By using the annihilation and creation operator, we exactly computed also the mean value and the variance of Q, that also have this oscillatory and confined character along time. So this analysis supports the fact that if we are dealing with a harmonic potential that depends on the anisotropies, we were able to avoid the growth of the anisotropies arbitrarily close to the bouncing point. And so far, we have demonstrated that the presence of harmonic potential is a necessary condition in order to maintain the universe in a quasi-isotropic state. But is it also a sufficient condition? The answer is negative, in the sense that if we consider a different behavior for the universe area, so not a bouncing solution, but for example a singular collapsing branch, we have that the variance of the anisotropies diverges in time. So our quantum state is completely delocalized, and we cannot infer anything about the constraining of the anisotropies or their evolution in time. In particular, if we start with a quasi-isotropic state for our universe, it is not ensured that arbitrarily close to the singularity, the universe is still quasi-isotropic, but it can be completely anisotropic. So, to briefly summarize, in this work we have reformulated the Vilenkin approach in the momentum representation to make it compatible with the polymer formulation. In particular, the use of the Vilenkin approach is important in order to recover a Schrödinger type time evolution for the quantum degrees of freedom. We have split the phase space into a semi-classical part and a quantum one, and decided to describe as quantum the anisotropic degrees of freedom. We have also implemented polymer quantum mechanics, and we have demonstrated that polymer quantum mechanics is able to reproduce a bounce when the universe area is chosen as discrete. We have analyzed the Schrödinger evolution of the anisotropies on a semi-classical bouncing background, and we have demonstrated that the presence of the quadratic potential for the Bianchi model is able to maintain the universe in a quasi-isotropic state. Also, we have demonstrated that the presence of the potential is necessary, but is not a sufficient condition, in the sense that if the background is singular, the quadratic potential is not sufficient to avoid the unlimited growth of the anisotropy. So the important thing is that thanks to the presence of this potential, we are able to introduce the polymer effects of the background at a quantum level. Thanks for the attention.
Thank you, Eleonora, for the nice talk. Questions, please?
There exist simple models of a scalar field coupled to gravity, where in the Einstein frame you have a bounce, but then there exist other frames where everything goes completely regular. So in these models you have, of course, full control of the fluctuations. Have you ever checked that your method really works well with this type of methods for this type of particular models? I mean, that would help a lot in order to see, if the approximations really work or not.
Okay, do you mean in other frames? Can you repeat the question? I think I don't.
Well, you are free to choose your metric frame.
Yeah.
So there are models where in the Einstein frame you have a bounce, as a real singularity, and then you go to a different frame, and there everything just goes smoothly through the bounce from one side to the other. The scalar field just changes sign, and that's it. So of course in these models, since the effective action for this model is known, you can compute the fluctuations, and you can really follow what happens when they go through the bounce, and that should be a good way of testing your approximations and your assumptions, because in this case you have full quantum field theory control of everything.
Yeah, okay. We didn't check, but The fact is that when you reproduce the bounds in polymer quantum mechanics, changing frame and changing the metric variable that you're going to discretize, it's a really subtle issue.
But not on the, not on the effective action. Once you have that, you can of course change variables.
Yeah, but it's not easy to do this when you quantize on a lattice, because the presence of the minimal length makes non-trivial the identification of the canonical transformations. So you're not sure if when you change the variables, you are doing it in a canonical way. This is not clear in polymer. That's the point, but it's obviously useful to verify if the results are conserved in other frames, but we didn't check this here. Thank you.
Okay, thank you.